First of all, I'd like to start out by making some thanks and acknowledgments first to the Amical Foundation for its maintenance of this award, so it's possible to obtain. The National Science Foundation for support of my work over a number of years. Also, two of my colleagues at the University of Wisconsin-Milwaukee and at the University of Pittsburgh for providing the kind of atmosphere and the facilities needed to do worthwhile research. Thanks to all the speakers, to Dr. Ishins for the program. It's been a great honor to me that this distinguished group were willing to stand up here and tell all those lies about me this morning. Each of these previous speakers, as you know, are people who are playing leadership roles in research which is of greatest value to the petroleum industry. Those kinds of things which can eventually lead to new processes, payoffs. I'm sensible to the honor attached to this award and greatly pleased to be this year's recipient, but the honor has to be shared with a large number of students who, as you know, did all the work. I'll mention a few of them by name as I go along, but there are many others who contributed indirectly, and although they were engaged in other programs. No one ever receives an award of this kind without a lot of help. I owe a great debt of gratitude to a large number of my friends and colleagues who have exchanged views on catalysis with over the years. The selection of the material for today's lecture posed a bit of a problem. I was suddenly, and to my great surprise, told that I was to be this year's recipient, and please, within 24 hours, could I give a title of my talk? And so I said, what have I been doing all this time? So I started to try to put something like that together, this relationship between surface chemistry and catalysis. I decided we had to put some constraints on this, or there wouldn't be time for the afternoon session. So, in thinking it over, we've been interested in a variety of catalytic systems over the years. We've tried to divide our work about equally between characterization and reaction chemistry. And so I decided that for the particular audience here, probably the latter, that is reaction chemistry, would be most appropriate. And besides, I wanted to illustrate a point which George just helped me make, that studies of reaction chemistry can tell us much about three of the key problems that we're faced with catalysis, namely the catalytic mechanism, the chemical nature of the intermediates and sites which form these intermediates. Because it's the chemistry that we want to carry out that is the thing that's going to benefit our society in the long run. Therefore, the theme of today's talk will be the reaction of simple hydrocarbons, principally the N-butenes, as diagnostic tools for the discrimination among mechanisms and intermediates. This topic will permit me to touch on a variety of catalytic systems with which we've been involved, and what I hope to be able to show you is that it takes simple reactions like this, and you can look for criteria which you could use, much like a medical doctor diagnoses a disease. One thing may not tell you everything you need to know, but putting enough pieces together, you can decide what the general course of the reaction is going to be, and distinguish it from others. It happens that the butenes can be isomerized by at least 4 different mechanisms. If I may have the first slide, I guess, do I have it here?
Maybe you got
Is the, well, is the light on?
it should go on when you hit the first one.
There we are, we're on. Several weeks ago, a feature article appeared in CNE News pointing out the potential of organometallic clusters for the development of bottled catalyst reaction systems. And I picked a sentence out of context there which sort of summarizes Joe Hagan's sales pitch. And whether you agree with this or not, I think there's no doubt that there's a considerable amount of current interest in this kind of approach, and so I thought it might be appropriate place to start. So the catalyst that we're going to use in this part of the work is shown underneath the dotted line there. It's triosmium dihydride carboxyl phosphine bound to the surface of silica gel catalyst. And this catalyst was prepared and furnished to us by Professor Gates, for which we are grateful. And I should hasten to add that Gates not only made the catalyst, but and characterized it spectroscopically, but also made a study of the preliminary study of the isomerization of 1-butene over this material, and concluded that his results were consistent with the idea that the secondary butyl alkyl was acting as an intermediate. Well, as I'll show you in a few minutes, it takes a little more than just studying one of the butenes to conclude something like this, but certainly he had every right to assume this, we actually adopted this point of view at the start of our work. This next slide simply shows the general characteristics of the isomerization of 1-butene when carried out in a static recirculation reactor at about 50 degrees centigrade. As the 1-butene disappears over a period of about 5 hours, you see the trans and the cis-2-butene pairing together. And you can see that from the very start of the reaction, more trans-2-butene appears than cis, but even after 5 hours, the trans-cis ratio is not at equilibrium. You still have more cis than would be present at equilibrium. Now, turning to taking a second butene, the cis-2-butene, pure cis-2-butene, and you isomerize this, and you again get a very definite trans-selectivity over 1-butene, much bigger this time. The thing that you might want to note on these slides is that from data of this kind, it's pretty easy to get fairly accurate values of the initial product ratios. So the kinetic scheme that we set up to sorry about that. I thought I was going to lose my voice last night anyway. The kinetic scheme which we set up to treat these data is shown here. Namely, we assume we have a common intermediate, and that the concentration of that intermediate is maintained by the reaction network which you see there. One can then do a steady-state concentration, steady-state treatment of this, and derive the rather simple equation shown in the upper right-hand corner of the screen. You might note, however, that if you start out with one of the pure compounds, and at the initial stages of the reaction, P2 and P3 will be quite small, and so because back reaction will not have become important. Now, we, of course, had previously determined that the reaction was first order in each of the compounds. Now, the rate at which one of these products can appear based on this scheme then is simply the rate constant between the intermediate and the product multiplied by the concentration I. And so that means that for dealing with the initial product ratios, you don't need to even know what that concentration intermediate is, because the initial, say, trans to cis ratio would then be just simply K minus 3 over K minus 2. And so this gives you a very simple way to get three equations involving those 6 rate constants. When we are concerned with the relative rates of disappearance of each of the 3 butenes, we have to take into account also the difference in enthalpy at the between the gaseous molecules. Well, if you can do these experiments in this way, you can take the 3 initial product ratios, you can take the 3 equilibrium constant ratios and convert them into the formalism of the scheme that I just showed you, and you can then pull out all 6 of these initial rate constants. Then if you take and plot the, according to the Arrhenius function, the initial product ratios versus temperature, because you can do these experiments with a number of temperatures, you can then get the differences in activation energies at the top of the barriers, which are shown on this slide. And so you can see then that platform is, in energy space, is meant to represent the energy of the intermediate, whatever it may be, and the products are formed by then escaping over one of those 3 barriers. Those are shown there are the experimental values we got by plotting those 3 product ratios. The ratios that we obtained ratios obtained experimentally are shown here. We can take those ratios. Let me go back. We can go back here and we can take these differences in activation energy, and we can make one further assumption. We can take those ratios of rate constants we have, we can substitute in Arrhenius functions, and then we can, in the case of the 1-butene trans ratio, we could put in the, this would be K minus 1 over K minus 3. We can substitute Arrhenius functions into that. We can then turn around and say, well, look, the pre-exponential function should be equal except for a factor of 3, which is required because to form the 1-butene, you've got to lose 1 of 3 hydrogens off of the terminal carbon. To form the 2-butene, you've got to look to discharge in particular. So, in this way, it's possible then to calculate just from these energies at the top of the barriers what that initial product ratio ought to be. you're going to calculate in the same way the initial reaction rates, we have to take into account these enthalpies down here as well. But it turns out the activation energy difference between, say, cis and here, or whatever reference you use, cancels out so that you can make those theoretical comparisons. Okay, now I'm getting back on the street. Okay, the point I want to make is that we're making then a couple of arbitrary assumptions, and they have to be justified by the data. And so we compared here at these 4 different temperatures, the selectivities, which we calculate, this is trans ratios, and the calculated versus those which we determine experimentally versus calculated. You see, the agreement is excellent. Okay, we can do this for each of these isomers, and you see that in all cases, the agreement is extraordinarily good. We can go on and look at the initial relative reactivities, and here too, you see now this is not, these are not quite as good agreement, but they're a better agreement than anyone has a right to expect. 9 to 2.5 to 1, 10 to 2.0 to 1, and so on. In addition, one can do a little bit more mathematical manipulation and can pull out equilibrium constants, which are based on nothing but the differences in the activation energies at the top of the barriers, on the experimental enthalpies that are taken out of the literature, and the assumption that we made about the cancellation of pre-exponential factors, and we can make a comparison between the experimental equilibrium constants, which we take, these are the ones we take out of the literature, these are the ones we calculate on the basis of this simple model. So what have we then accomplished here? We have shown, first of all, that over this reaction system, that the data all conform to a common intermediate. We found that the product selectivities and other properties are controlled by the differences in activation energy for the reaction. But does that really tell us that we have established that we have presently 2-butyl alkyl intermediate? And the answer is, well, no, because the same results would have come out if we assumed that we had a carbonium ion reaction. So how can we distinguish between those features? Well, let's consider the following. The carbonium ion versus hydride insertion mechanisms. First of all, if you carry out experiments where you co-isomerize equimolar mixtures of C4H8 and C4D8, that you'll find that both of these are intermolecular processes, because what will happen is you'll have immediately after the start of the reaction, the surface hydrogens that are functioning in the reaction will be about equal H or D. So one of these two molecules comes down to the surface, and it has about an equal probability of picking up an H or a D. And to undergo isomerization, it must discharge a hydrogen from a different position in the molecule. So that similarly, if the other the deuterated olefin comes down, it has an equal probability of picking up an H or a D, and to undergo isomerization, it has to discharge the opposite from another point in the molecule, so that the surface sites are maintained about equally H and D. And there's going to be an intermolecular transfer of an H or D for every molecule isomerized. Now, let's consider 1-butene over an acid catalyst. Over an acid catalyst, the proton or deuteron will inevitably go on the terminal carbon because of the greater stability of the secondary ion. And consequently, when after isomerization has occurred to 2-butene, you will have the deuterium left on the terminal methyl group. By the organometallic mechanism, if you add on a D to 1-butene, it can either form the primary alkyl, which puts the D on the 2-carbon atom, or it can form the secondary alkyl, which puts the D on the terminal carbon atom. Now, the former here is not cannot lead to isomerization. It's not an intermediate for isomerization, whereas the latter is. But the former can act as an exchange mechanism to pump D into the molecule in the internal positions. The consequences with the 2-butenes are similar. Now, we then made you see, we took advantage of this and made comparison of several experiments where we co-isomerized cis D0 and cis D8 equimolar. And we carried these out over silica aluminum cracking catalyst and triosmium cluster catalyst. Now, as you expect, the reactant extrapolates back to 0 at 0% conversion. We plot a number of H or D atoms exchanged per molecule because there's no exchange with the 50-50 mixture of C4H8 plus C4D8. The product molecules, though, as you see, you'd expect them to be formed with initially at least with about 25% D0, 25% D1, 25% D7, and 25% D8, so that the number of atoms exchange, H or D atoms exchanged per molecule is just about a half. And those data extrapolate down to that point. These are for the trans. When we go to the 1-butene, where we expect to find more exchange taking place with the triosmium system, you see how it very much deviates, although it comes to the same intercept down here as it should. Now, we took samples of the 1-butene, and through the courtesy of Bob Uskowski in Michigan, we got microwave analyses made of these. And what we found was over silica aluminum, the exchange occurred only at the terminal position on C1, as you'd expect within his experimental uncertainty. Over the triosmium complex, however, where this extra exchange possibility exists, he found that he had exchange at both C1 and C2, and the ratio at C1 to C2 was roughly 2. So in this way, it is possible then to distinguish between the two mechanisms. I wanted just to say a couple of words about the acid catalyzed mechanism while I'm here. This is a very old slide that Joe Hightower and I concocted back about which shows a carbonium ion on the surface. If the idea was that for a trans, if you could discharge H sub B from C3, you could form the cis by discharge of H sub A here from the same carbon atom. So we expected no difference in activation energy, and you ought to get a cis-trans ratio close to unity and temperature independent initially before secondary reaction takes place. Back here, to get form 1-butene, you got to discharge 1 of 3 here, and we expected that this activation energy might be higher, although it would be partly compensated by these. The reaction coordinates, which were used at that time, are shown here, and you see they're a little bit different from those from the triosmium complex. In particular, we actually observed no difference in activation energy at the top of these barriers here, or escape from the carbonyl ion to the cis and trans products. This was 0 in the experimental air, whereas the top of the barrier to go to 1-butene was about 800 calories higher. A little while later, Lombardo carried out a study using a very weakly acidic sodium Y-zeolite. This was the sodium Y-zeolite, which the simple expedient was used to take out a little bit of sodium, create a sodium deficiency by simply extracting it with a socket extractor for $1 or something like that. Anyway, what was observed was that there was no difference whatsoever at the tops of these barriers. The activation energy was somewhat higher than found for the silica aluminum catalyst. So there was no, so that we see here that you can have the same formal intermediate, but it will have different reaction chemistry on different surfaces. And this suggests that it should be possible to, at least in a limited way, to control product selectivities, because through use of this factor. You see, the carbonium ion, or I guess I should say carbenium ion, can differ by the activation energy forming and by the differences in heights of the barriers, if any, and in the stabilization energy epsilon at the top of the barrier. There's no direct way to measure epsilon, although you can see effects of it, of this in some of the reaction chemistry. The comparison of the results, similar to those I showed you earlier, are shown here. The comparison is about equally as good, and I won't go through it in detail except to point out a couple of points. Cis-trans ratios were unity and close to it, and temperature independent in all cases. In the case where there was no difference in activation energy, you'd expect that statistical factor of 3 turn out to be it actually seems to be pretty close to it. The Sono carried out a number of experiments using various metal sulfates adsorbed onto the surface of silicon gel. And I just wanted to show you here how well some of his ideas and data fit in with some of ours. Namely, he had a weakly acidic catalyst, which was the magnesium sulfate, and he converted these into catalysts by adding some water vapor into the system, so the hydrolysis produced some acidity. And a strongly acidic catalyst has a lower activation energy. Note also that the tops of the barriers between one butene and the other two split, whereas they don't split very much here. In fact, this kind of reaction is almost, can become almost concerted. Now, the interesting suggestion for some made is that as you pull the top of the barrier down, you also pull down stability of the stabilization energy from that stable state, so that the carbonium ion will live longer in this state and have a bigger chance of undergoing secondary reactions. So, what one finds then in criteria for this acid catalyzed reaction is, again, it's an intermolecular process, and it has cis-trans ratios which are close to unity and temperature independent. The 1-butene cis and 1-butene trans ratios will vary with temperature and will vary from unity because of the difference in activation energy that comes in here. All right, now we've talked so far about two kinds of intermediates that the 1-butene molecule can undergo going in the isomerization reaction. When one plots up the data that one obtains from a number of different systems, one finds that got this temperature-independent unity ratio, and this works for the molybdenum aluminum catalyst for the acid catalyzed reaction to the fall right on top of that. But then you have these other group of things that have high ratios and which tend to decrease with increasing temperature. What can be said about those? Well, I think it was Hahn and Pines who first noted for aluminum this high ratio, and they suggested that maybe there was an additional pi complex came into here. When Hightower and I finished our work with the acid catalyzed reactions, we said, well, now we know how a Brunstad catalyzed reaction ought to look, and what will happen if we try aluminum. We tried aluminum, and we found that we reached a couple of conclusions. One was that we could not explain the data based on a single common intermediate. And secondly, that the reaction appeared to be intramolecular. Instead of, so that you have a movement of the hydrogen inside the molecule without exchange with other butene. Okay, now it remained for Kokas to show us what really happens in a system like this. Kokas on zinc oxide was able to demonstrate the presence of the pi-1-butene, the pi-cis-butene, the pi-trans butenes. There were three different infrared bands corresponding to these three different pi-bound butenes. Then there was a slow conversion into the syn of the anti and the syn pi-allele species. These, as you see, had to be formed by extraction of an H or a D off of the allele position. So this is proton transfer in the reverse direction. form these intermediates. In addition, Gogas describes some interesting chemistry, namely that he confirmed the work of Pliskett and the Ishams that zinc oxide would dissociate hydrogen to form ZNH with OD. Those, of course, can be seen in the infrared spectrum. And then he further showed that, given this ZNDOD, that it was possible to react this with olefins to insert and form the zinc alkyl with the deuterium on the terminal carbon with the OD, and then a slower conversion into the 1,2-dideuterioalkane. Although K2 was smaller than K1, it was much bigger than K-1, so that this alkyl intermediate for zinc oxide did not function as an intermediate for isomerization, as might be expected. It also meant that there was no isotope mixing from going back and forth between them. Stepping down to step 4, we see that in the absence of hydrogen, the olefin can react with the same sites that produce the dissociate hydrogen to form this pi allelic species with an OH. And this species can go back and forth and can therefore act as intermediate for isomerization. We followed up on this work a little bit, carried out 2 identical experiments, the same static recirculation system, using the same zinc oxide catalyst. In one case, we simply used the 1-butene as the reactant and followed the course of the reaction. We found, and this is solid, the dashed lines, we found the high cis to trans ratio, which was expected. We then did the identical experiment, same amount of butene and everything, except that now we added in also an excess of deuterium, and we carried out the reaction, and the rate of disappearance was not a bit different. The rate of reduction of the cis and the trans were diminished, but the same ratio was present, and the difference was exactly made up by the fact that we were forming butane simultaneously. Now, this is a very interesting point, because it says that exactly the same sites which are carrying out carrying the reaction for the isomerization can also carry the reaction for hydrogenation. It's just a case of hydrogen gets there first and wins the sites, then these react with olefin to form the alkyl intermediate, which goes on to form the alkane. It does not revert over to the catalyst. And on the other hand, if the site is empty and along comes a butene molecule, it forms an allelic species. So that we have the same surface sites carrying out different, apparently different functions simultaneously in the same reactor in a competitive way. I wanted to show you some further results, tracer results, which we carried out with zinc oxide. And I'd like to compare them first with the data of Morel over here in Poitiers. And I'll say right off the bat that for this first reactant, cis 2-butene 2,3-D2, going to the 1-butene and trans 2-butene, the products, everything are exactly the same in both cases. Namely, that this olefin, which is labeled in the internal position, the methyl groups are per hydro. There's no isotope effect, and you wouldn't expect any, because you're just removing H from a methyl group to form the intermediate. The same thing was found for Morel's aluminum. Now, we had previously been using an aluminum which was made very highly pure from the neutral hydrolysis of aluminum isopropoxide. And here we got no isotope effect, but we got a lot of mixing, a lot of scrambling. So it took quite a little bit of research to be able to conclude that this scrambling is not due to the isomerization mechanism. It's another reaction that takes place. In fact, we found we could exchange CH4 with CD4 over the catalyst. We could make per deuterium cyclopropane by exchanging cyclopropane with hydrogen, with deuterium over this catalyst. Okay, Morel did an experiment that we did not. He went to the trouble of labeling all the methyl groups. So he used cis-2-butene 1,4-D6. And in this case, you see the process is entirely intramolecular, no scrambling, and but there's a very large isotope effect. And we observed the same sort of thing when we compared our cis-2,3-D2 with cis-D8. We found that the cis-D8, where the methyl groups were labeled, was about 4 times slower than the case where the methyl groups were hydrogen. So here we see then a third type of behavior that butene can undergo, namely where the proton transfer is to the catalyst instead of away from the catalyst. The reaction becomes intramolecular, and there's the high cis trans ratio and so forth. Interestingly, Gary Haller reported several years ago some experiments over chromium, where also these same characteristics were exhibited. Namely, he used propene, labeled propenes instead. You could follow the isomerization by the intramolecular movement of H or D inside of the molecule. So it would look like chromium catalyst can isomerize, can react involving the elytic intermediate. The interesting thing is that if we go over to the molybdenum aluminum catalyst, this does not happen. This is a sulfided molybdenum aluminum catalyst. You might note that the general characteristics are very similar to those of the tri-osmium system. When you're isomerizing 1-butene, you get a very severe, in this case, actually a ratio that goes to unity at 0 time, and you get this big trans selectivity that you saw before. Carrying out the C4H8, C4D8 mixing experiment, one sees that the results conform to the intermolecular process. indicating that this reaction goes through the alkyl type of intermediate, and exactly the same thing was observed over molybdenum disulfide by Naga. We have a little additional support for this in that we decided to test the effect of hydrogen, adding a little hydrogen in, not enough to completely hydrogenate the olefin, but to see what effects it would have on the reaction. And you see that the reaction rates were very substantially increased from something going like this to something that goes like this. A lot of this was due to the formation of butane, but as I'll show you in a moment, these rates were also considerably increased. This is for the cis-2-butene. Similarly, this rate for the cis-trans jumped up so much that it reached equilibrium at 15 minutes. And yet the general selectivity pattern was retained. This table compares the reaction rates for these experiments with those where no deuterium was added in. These are shown in the parentheses. Note that the consumption rate is very much higher than the sum of these two numbers. In all cases, order of magnitude. Note also that the actual production of the olefins is much increased, even though much of the reaction increase takes place because through the hydrogenation to butane. So we see that in the molybdenum system, that the amount of hydrogen that is present in the system or on the catalyst will very much affect the amount of alkyl you can form and very much affect the rate of that reaction. In fact, you might ask yourself, how do you carry out an alkyl mechanism over a catalyst like a molybdenum catalyst? Where does the hydrogen come from to form the alkyl? Well, it must be hydrogen that's there that you can't remove after the catalyst is prepared. And if you add a little extra in, you can pump things up quite a bit. In the case of the chromium catalyst, where the allele mechanism was shown, we carried out some experiments with that also, discovered that we could change it from one pathway to the other by the amount of hydrogen in the system. Well, I wanted to finish up by talking a little bit about the final way that you can isomerize butanes, namely by olefin metathesis. And there's some interesting chemistry that's evolving currently in the literature, which is very helpful in understanding what has been called sometimes in the past the reactions of hydrocarbons over some systems and organometallic zoo. First of all, an olefin can indeed form an allele species with the molybdenum sites, if you like, but this species appears to revert rather readily to the metallocyclobutane. This metallocyclobutane then can undergo cleavage to form an olefin containing less carbon atoms than the initial olefin, and the anion surface carbene
species. Similarly, we have found that you can take cyclopropanes and they will form this metallocyclobutane directly, just by insertion into the ring. And when you get to this stage, one of two things can happen, and usually both. Namely, you can pass on to the allele, to the olefin, and you have isomerization, or this thing can cleave to give you an olefin and a surface carbene. The surface carbene, of course, is going to be useful in olefin metathesis. I wanted to discuss with you some data that we obtained from reaction of methyl cyclopropane in the presence of hydrogen over reduced molybdenum aluminum catalyst. Now, this says hydrogenolysis, but I think it's a misnomer. It should probably be isomerization followed by hydrogen. The scale for the methyl cyclopropane is over here. Okay, as the methyl cyclopropane disappears, the two principal products formed under this condition where we have excess hydrogen in the system together with the methyl cyclopropane is propane and butane. And there's smaller amounts of olefins and some isobutane is found down here. The question then comes, why would you get such a distribution of products? Well, the fact that you are getting this C3 product suggests that you must have had some metathesis or cleavage of a metallocyclobutane to get rid of that other carbon. The next slide here will show you what you might expect if you were carrying out metathesis and the isomerization of one butene over these reduced molybdenum aluminum catalyst. And of course, you expect isomerization to occur by the alkyl mechanism, and but at the same time, it's possible for some sites which are not occupied by hydrogen to react with the olefin to form the allele. The allele forms a methyl cyclobutane. The methyl cyclobutane then can undergo cleavage in two ways. One, to form propene, which is on hydrogenation will form propane, and also some ethene. There's no way to decide a priori whether one of these two methods of cleavage is favored over the other. But whenever this happens, you've got to leave the corresponding carbene on the surface, and so I call that carbene 1 and carbene 2. Given this bank account of carbenes, it's then possible for the 1-butene to react with the carbene 1 or carbene 2 or carbene 3 with the resulting formation of C2, C3, C5, and C6 olefins, plus the carbene surface species, regenerated carbene, the surface carbene species 1, 2, and 3. Now, at the same time, because we are having isomerization that we're forming a lot of 2-butenes, and the 2-butenes are very effective in reacting to form propene and species 2. And if you have species 2, 2 butenes will react with it, give you back 2 butenes, and so on. So this is some of the chemistry that allows you to get some of the kind of strange product distributions that you see in the system. The fact that you get isobutane in here means that when you insert, you could get a different metallocyclobutane than the one here. You get this one most of the time, but you can get one with the methyl group on the far side, and that will give you the isobutene. Well, in closing, I wanted to just tell you about one kind of interesting experiment and point out a way that you can always spot olefin metathesis if you carry out your isomerizations with equimolar mixtures of per deuterium per hydro olefins. Let's consider first the reduced molybdenum catalyst over here. We're going to use a pulse experiment. We pass a single pulse where initially we had, before we, the blank pulse, we consider you these 2 points here and one there. But first pulse that passes over the catalyst, you see you get approximately equal amounts of D0, D1, D7, and D8. Okay? This is kind of what you expect for an intermolecular mechanism through the alkyl intermediate. Note, however, first pulse passes over the catalyst, you see you get approximately equal amounts of D0, D1, D7, D8. Okay? This is kind of what you expect for an intermolecular mechanism through the alkyl intermediate. Note, however, that you see a little peak here at D4. That means half the molecule is per hydro, the other half is per deuterium, which must have been formed by olefin metathesis. Between this first pulse and the second pulse, approximately 20 minutes elapsed while the system was washed out with helium, and then a second pulse was put in. And now, all of a sudden, we get a big spike here, which apparently was due to the fact that there's an induction period to form the carbene species, that you got more carbene centers by the time you got the second pulse over the catalyst than you did the first. Finally, we said, well, let's give it a good dose, and so we put 300 torr of butene on the catalyst, let it sit for 5 minutes, flushed it off, and did it again, and nothing much happened. Well, the significance of that is over here. If we use the oxidic form, where the molybdenum was all molybdenum plus 6, we could still get a slow isomerization process, which makes an acid catalyte. But the first pulse, when you analyze the trans-2 butene that was actually formed, you got this kind of a distribution. The same thing, the slight tendency to show a little bit of metathesis in the second pulse. But then when we soak this thing for 5 minutes at room temperature in butene, flushed out the butene and went back, we got the most selective metathesis reaction we yet see. So it's kind of interesting. I think Koblinski observed something similar to this a while back, that you can activate one of these catalysts in a very high valence state for olefin metathesis by simply treating it with butene gas. So, in summary then, I hope I have stumbled through this thing to the extent that I can have shown you that you can get a lot of information about sure the